All right, welcome everyone to the collaborative learning meeting. This is our second new time slot, Wednesday afternoon, 1 p.m. Eastern at WPI. We're also using the Skype for Business, so if there's any technical questions, feel free to ask away. We're joined again by Professor Jim Duggan for the second time for the follow-up on his presentation of using system dynamics modeling with R. Pleasure to have you again, Jim, and I'll go ahead and hand it over to you.
That's great. Thank you very much. Delighted to be here again, and looking forward to the talk. So what I have is really just to go through the remainder of the presentation that we started a couple of weeks ago. So just the first slide there shows the overview of both presentations, and the last week we got through R and data science, looking at R as a tool for manipulating data and exploring data. And then we looked at system dynamics modeling with R, and the first part then was modeling using DE-Solve. So basically it shows a way where you can actually build an SD model inside of R, although it's not an essential requirement to do that, because I think someone at the last meeting used the word post-processing, which I think is a very nice word to use with R, because any data you have from your own models, whether they be VentSim or Stella or any other type of any logic model, etc., you can create the data set and process that in R as well. So basically we looked at running a simple model in R at the last session, and today then we're going to look at looking at behavior modes, which essentially is using the graphical power of R to visualize the behavior mode of a time series. I looked then at disaggregate models. In R, you have nice support for vectorizing models, and there's a particular example using the SIR model, which I think is very interesting. Then we look at sensitivity runs in terms of running many simulations with changing the parameters. Then to look at a common technique in SD, statistical screening, which again we can use to help identify the influential parameters for a given set of simulation runs. And the final topic then is R Shiny. If you want to, as it were, create a mock-up of your simulation, make it available on the web, there are tools in R that allow you to do that, and the R Shiny system is quite a nice way to put your presentation together and make it interactive for other people to use. So that's the overview of the talk today. Okay, so behavior modes then. It's really looking at a given output behavior over time. So here we have a diagram of of exponential or S-shaped growth. It's a simple one-stock model that we're all familiar with. And what we can do then is, as it were, when the model is finished running, we can do some post-processing on the data, and then we can add extra information to the data set. So our overall understanding of exponential atomic behavior pattern is the second derivative of the absolute value of x over time. If that's greater than 0, we have exponential an exponential ABM, atomic behavior mode, and if it's less than 0, we have a logarithmic one. There are many ways to do this. This is based on Ford's method of just looking at the inflection points and characterizing the behavior over time. So what we could do in R is we can write a couple of okay functions that allow us to do this. So I think one thing, if you are using R, it's very useful just to get used to writing quite simple functions that allow you to process the data in different ways. So basically 2 lines of code to get the derivative of the time series, and I tested this against the deriv n function in Stella, so we get similar results there. And there's a diff function in R, allows us to get the difference of different values, and we have the variable of interest and the time. And then we can then use that result to get the atomic behavior mode, where we take in a processed value, and if it's equal to 0, it's linear growth. If it's less than 0, it's logarithmic, and if it's greater than 0, it's exponential growth. So this is, and again, all this code is available on the GitHub website, but it just shows you if you want to do some post-processing within R, really all you got to do is write those couple of functions, and what we can then see is by just calling these functions with the net flow variable, with the absolute value of that, we get a new variable called the ABM, which is a numeric value, and then we convert that to the B mode, which is like a categorical variable. So the point here is that we can use the power of R to add, as it were, new features to our data set, and the feature then really is the behavior mode of a variable at a certain point in time. And I think if we can you see my my cursor there? Maybe I'll use this one here. So, okay.
No, I don't. We can't see your cursor.
Okay, so so what I'm kind of trying to point to there is, if you look at the plotting function, there's a plotting parameter saying color equals $O$B mode, which means that the graph will draw a color based on the different values of that variable. And because B mode is a categorical variable that has only 3 values, which are linear, log, or exponential, it will then create your graph and then very quickly show you how the like the inflection point, and you can add this extra information to your graph. You can do this again, as I mentioned, either as it were natively inside R, or you could take your data set from a Vensim run and do the same kind of analysis, which goes to I guess support the view that R can be a very valuable tool to communicate the results. And just by writing these 2 simple functions, we can get this extra information, and then we can apply this to any variable in the model, and straight away we don't just get a behavior over time, but we get it broken into the different parts of the atomic behavior modes. So I find that a very useful way just to look at the data and capture the results.
Will it do that, Jim, real quick, will it do that in like an oscillatory? It will show as it goes up and down? It'll break it into the atomic parts on a continual oscillation?
It should, yeah. I mean, once you can mathematically define the behavior at a certain point in time, because that will be a separate column for each time point, it will then pick up that color. So for example, I think in the textbook I've that done for the infection curve, the kind of bell-shaped curve for infection, and it breaks it up on the way up and on the way down again. So basically, anywhere you classify your data point as having a certain characteristic, once that's a categorical variable where you say it's either linear or log or exponential, it will then pick up the appropriate color on the graph. So it will do that. Okay, just trying to find out. Getting back to here again. Okay, so yeah, so that's behavior modes, and again we can use that in a post-processing way or within a native model inside R as well. Okay, the next one then is, and again, if you have any questions, please stop me as I go along. So that was behavior modes, and basically coloring your notation your graph to give extra information. We can now look at disaggregate models, and I think what's interesting here is when you look at the code on the right-hand side, you can still have one equation for every dimension in the model. So the model that you create doesn't get overly complex, but you can, in terms of writing equations, but you can, as it were, subdivide it into different dimensions quite easily as well. So this is a disaggregate model it's the SIR model across cohorts. And this model is useful if you want to, for example, simulate maybe vaccine interventions where you have different young, adult, and elderly, where you have different maybe immunities, different contact rates. We can break out our model in this way. So it could be very useful, for example, if you wanted to figure out if you've got a scarce supply of vaccines, who should you vaccinate first? And this model allows you to explore this in more detail. So the stock flow model is on the left-hand side, and essentially it's just like a replication of SIR for the 3 different cohorts. We could also use a spatial model for this if we wanted to model the spread across a geographic area. It's a conventional kind of the meta-population way of doing the SIR model. So I think we call it disaggregate models, but I think in the medical kind of modeling area they would call them meta-population models. So we can implement this in R quite conveniently as well. But underlying it all, we use matrices just to calculate the force of infection, which is your rate that will actually turn people from susceptible to infected. What's nice about the underlying equations for this is that it fits neatly into matrix form, which means it's very, very scalable as well. So R has a very good support for matrices, and basically if you have a lot of subpopulations, you can bring in data from Excel, for example, put it into matrices, and then this matrix equation becomes part of your solution, which means that it just simplifies the overall solution process when you put the R model together. So that's, I guess, the mathematical model that we use for the force of infection, where again we have lambda, so that's lambda y, lambda a, and lambda e. We then, like in the model itself, it takes a little bit of work, I suppose, because you have to identify 9 stocks instead of 3. But again, all this code is available on GitHub. We have a stocks vector where we have the name of the stock and the initial conditions. So when we're using DESolve, which is the library within R that is used, we define all our state variables in one single vector. And so that could be quite small for a small model, but theoretically, if there was 1,000 variables, you would have 1,000 you have 1,000 elements in the vector. The sequence here is important because we first define all the susceptibles, then the infected, then the recovered, because when we write our model itself, we have to, as it were, deconstruct that particular vector into matrix form. And the delays then are very simple: 2 days for young, 2 days for adult, and 2 days for elderly. But they're the model variables, and that's how we define our stocks. And this is the actual code itself. So what DESolve will do is it takes in a vector of all the stocks, which is a vector of, as it were, 9 values. But then in R, we convert that to a matrix. So the first line of code there is states is a matrix where we take in the stocks, and we have, as it were, 3 rows and 3 columns, where n row is the number of cohorts. And this is where it is quite flexible to extend it. So if you had 100 cohorts and maybe 5 different states, this code would still work because you just define those values outside of the function.
This may have been covered, Jim, this may have been covered in the first presentation, but do you find it more useful to create the model first, then do the R work, create the model a little bit, then do the R work in more of an iterative process? What's the development process you use for these?
Yeah, that's a good question. I think it depends on the complexity of the model. So, for example, we would have worked on a model with colleagues in public health where it was very, very detailed model that I had to do in Vensim first, and then we have a converter from Vensim then into R, because I think the model in the end had 120 equations, and I think if you had to type all those into R, it would just be a nightmare. So for that scenario, we built the model in Vensim. And then have a simple converter that takes all the equations and then actually puts those into this particular function. And I think we got 90% of them okay in the first time. So that's a really good point, because if the model is quite large, you know, I suppose model building in R is like coding. So you still put in the equations, but you have to figure out, you know, is the order right? And that's why, if you use tools like Stella and Vensim that can actually output in computational order, and then you can run that through a simple converter that we have, you then actually get the equations in the right order. But for something like this...
So you have a utility that would convert the equations into R. How would you convert the graphical functions? I noticed that the graphical functions have some logic code written into them.
The graphical functions in the model, is it?
Yeah, if you first program the model in Stella or Vensim, and then use the utility to convert the equations into R, how would it convert the graphical functions?
Like table functions, it wouldn't convert them. You'd have to go in and do those in R yourself. So R has a thing called a prox fun, which is it does interpolation across input and output variables, but you would have to do that yourself. So like the software we have written is quite basic. It just gets the basic equations, but if there are equations that R doesn't recognize, you'd have to go in and edit those files yourself.
So if the model is written in differential equations,
yeah,
those could also be converted into R.
Yeah, what we have on the GitHub site is if you go into VenSim and if you print all your variables in execution order, computational order, and you save that to a text file, we have software that will convert that text file into an R file. And if R recognizes all the functions that you use, it'll run straight away. But if there are some functions in VenSim that aren't in R, then you just have to go in and change the code.
No, my question was that if you go into equations for Stella or VenSim,
yeah,
the equations are written in integral form.
Yeah.
The stock equations are written in integral form. If, like in MATLAB, if you start with equations in differential equations, and I see, although I don't like it, a lot of the papers are now describing their models in differential equations.
Yeah.
They first develop the model in stock and flow version and then convert it into differential equations. So if they throw differential equations, could those also be converted into R?
Yeah, well, I think, you see, on the slide there we have ds dt. That's really just the integral equation. So for using this utility in R, you just have to put your integral equations at the end of the function. So, for example, ds dt is minus IR, di dt is IR minus RR, and they are, like, if you look at, they're really equivalent to the integral functions in VenSim. So the utility in R then is it's really integration that it works off. It's where those particular equations like IR minus RR, they are directly taken from the VenSim output. So, does that answer your question?
Yeah. Well, my question was that if I did not use the system dynamics notation, which is writing equations, stock equations as integrations.
Yeah.
And I wrote the equations as my colleagues in the math department would do, like the differential equations.
Oh yeah, yeah.
Could they be converted into R directly?
Like my utility.
MATLAB, the other program that's used here. I don't use that program. I don't know how it works, but I understand that you could write differential equations and then the program will process them.
Yeah, well, I think that this R utility is used by a lot by ecological modelers as well, and they would formulate their equations as differential equations, and they still use this tool to actually generate the results.
So this is basically for generating an output and presentations based on the models, whether they are programmed in VenSim, Stella, or in terms of MATLAB type notation.
Yeah, so the model. So if you've written the model in MATLAB or VenSim, you would still have to go and write a version of the model for R. But what we see here is generally the analyst would have to write a function like this in R, but then the package in R, which is called DESolve, will then go and call this and generate the required output. And the actual package in R, when you run it, you can use Euler or Runge-Kutta 4 or Runge-Kutta 2 and specify your time steps. So basically, it allows you to do what you would do in VenSim and Stella. But what we're seeing here then is that within that function, you can actually make a disaggregate model as well. So this model is actually the SIR model across.
So in terms of generating the output, what are the additional advantages of using R? There is a sort of output which is generated by Stella and Vensim.
Yeah.
So what additional resolution does R provide?
I think in terms of, well, firstly, I think R is open source. So any of the advanced algorithms that you would have to pay for in AnyLogic and Vensim, you can get those for free in R, which I think is good. The other thing is R is very powerful for graphics. The ggplot function is very powerful for presentation. Really, and also if you want to do sensitivity analysis, you could do that in R as well. But really, I suppose, I mean, that's a really good question. I mean, at what point is R, I think it might depend on the problem that you're addressing, the tools you have available to you, and maybe whether you want to do a lot of calibration and data analysis as well. But I think a lot of what we're covering here today, probably the ggplot is something that everyone could use no matter what package they're using, because they can get the results, simulation results, and visualize those. But a lot of the other techniques are very useful because they're open source, and that means that you don't have to incur the cost of having an advanced version of existing tools to actually do some interesting analysis. And so I think the barrier to entry for doing additional analysis is very low with R because of the cost factor. But R does also offer, I think, very good visualization, and also the potential to use other, say, machine learning techniques, which can be used to analyze data as well.
Now, how would this visualization compare with the current utilities which are available in both Vensim and Stella, that you can export the output to an Excel file, and then you can do whatever you want with the data that's exported to the Excel file?
Yeah. I think, I mean that's a good question. Like for many things there wouldn't be maybe an obvious advantage, but I think for things like if you're let's say if you want to really produce very high resolution graphics, for example, you can create files that are maybe many megabytes of resolution. So for publications and that, R can be quite good. But also if you and we cover this, there are techniques in R where you can actually use things called, you can color on categorical variables, and you can do heat plots and lots of these things that are quite very useful for exploring data. But I mean, the tools out there are really good. I mean, tools like Vensim and Stella and AnyLogic are very powerful tools. And I guess the value add for something like R, I think, is the open source nature, but also in terms of presenting results. Like as we see later on as well, it also offers a way to visualize your simulations on the web. Although a lot of the tools do this as well, a lot of the modern tools do that as well. So I mean, it's a good question. I mean, I think myself, it's the open source nature makes it attractive, but also it is fast and powerful for doing post processing and looking at data in that way.
Jim, is that converter available somewhere?
Yeah, it's on. Yeah, it's on the GitHub site. So my GitHub site is there's a folder there called Reader.
Okay, I have that actually in front of me. So
yeah, so in there's an example of the code and how to use it.
Okay.
But what you have to do before you use it is to export the equations in computational order.
Okay.
So it's if you do that, then you can actually see how it works, and it should, like if the model is simple enough, it'll create an R file that you can then run and give you results like that. So
great.
Yeah.
I'll try that later. So
yeah, do, and again, with anyone, I'd be happy to answer emails if people if you get stuck at things and things mightn't work. But it's really just the utility is useful because it means if you're doing a model, you can speed things up because obviously coding a model is quite intensive.
Okay, thank you.
Great. So then we can do our graphs in R, and maybe this shows you like in R we can color the output based on the cohorts. So output like this can be generated quite easily, and this shows the Epi-Curve output of the infected population over the 3 cohort model. So that's Disaggregate Models, and because R supports vectorization, we can but again with other tools like Vensim and Stella, etc., you have arrays, and it's really no different from that. But it just means that you can do it in an open source way. And again, if you like coding models as well, you can actually go in and put all these together and use the speed of R to process the data. So that's Disaggregate Models. Any more questions in that section? Okay, I'll move on then to sensitivity analysis. And again, the preamble here as well is that, of course, these tools are available in conventional SD tools. And again, this package is useful. It's a package called FME, which stands for a Flexible Modeling Environment for Inverse Modeling, Sensitivity, Identifiability, and Monte Carlo Analysis. So there's a lot of stuff going on in there that you can use for your models. But basically the idea here is that we have, for example, a model we want to run. We want to vary key parameters and basically store all the output. Perform any simulation runs, analyze the output, and okay, so that's really the goal. So again, sensitivity is very powerful because it means we can look at parameters and see the influence they have on the variables. So from a technical point of view, this you create an R source code file. There's a model in there, but inside the model then is inside a thing called a simulation function that's called every time we want to run a simulation. So this example is also on GitHub, and the only difference really is that before we had one model function, but now we embed that inside another function, and then we call that every time we want to run a simulation. So it's just the process here is, if you're using another tool, you just go run sensitivity, how many runs do you want, and the program will run. But here we just put it all into our code, and again we can call the model, run it many times, and then we can put all the results in a very large data set, and then we can process the results. Okay, so here is an example of using, and again, I suppose we're looking at the at writing some scripts for this, and in using the FME package, all we need to do is to identify how many parameters we want to vary and what is the minimum and maximum value of those. So in the example here, we have CE stands for the effective contacts. We say the min is 0, the max is 7. DEL is the recovery delay. The min is 0 and the max is 10. And then the initial people infected in the model, in the SIR model, that is 1, and the maximum number is 25. So this is what we're saying is that there are 3 parameters that we're varying, and this is the range of the parameters. And what we need to do then is just to write some short scripts to, as it were, create a data frame, which is like a worksheet in Excel, where we specify the min and the max with these values in it. And this then we then send this into a function that will generate our random numbers. So basically, again, I suppose a common theme here is it's not exactly user-friendly, but because you have to go in and just type in these instructions yourself, but then you can run the script after that, and that will generate the results. So we put in these parameters. So there are 3 parameters. We say n runs then is 10, so we run the simulation 10 times. And then what we do is we create a new data worksheet or a data frame that has, for every single run, and using the Latin hypercube method of sampling, it generates the parameter range for each of these. So going on to the next slide, we can see then the input data frame is shown as the min and the max for each of the values. But then we have a data frame with 10 rows in it, and every row then is the configuration for every simulation run. So we're saying the first time we run the simulation, the contact rate will be 5.435887, the delay will be 4.63, etc., and the init infected is 13. So we're using the tool then to generate the random numbers, and then we put all those into a data frame, and then that data frame is going to drive our simulation. So there is a programming overhead here, because in our script we have to write all this code together, because what it's going to do is generate the random numbers, put all those into a data frame. And again, as I mentioned the last time, a data frame is simply like a spreadsheet, a number of rows of the number of observations. I'm sorry, I just need to turn off my email because it keeps coming in there. So what we then do is, we need then to just run some OR code. So we have, for every row of data, we need to run the model and store the results. So there's n simulation runs. Okay, that's the code itself. So we have a model file inside an outer function, where the outer function is called every time, and the input data then is the particular row of the sensitivity data. So basically we just send in this every time, okay, that's the model itself. But basically it's similar to what we covered the last time, except this file then this function is within another function. So once that's set up, I mean, I know I'm probably skipping through this a little bit, but the key thing here is that in order to run the simulations then, we just have to call one line of code. So you see the file, the line down towards the end where we say out is apply p bracket 1, and then we define the function x, and then we go run sim with x. So this is where OR can be quite useful, because we have these things called vectorized functions, and essentially we can write a very short piece of code that will operate on every single row in the data frame, where the data frame contains the run number and the sampled values for each parameter. So this apply function takes a number of parameters. So again, it's a bit like MATLAB, where you go in and write code like this. But the apply function will take in a data frame. The second parameter is 1, which means we operate on every row. And for every row then we call the function runSim with the values in the row. Okay, so basically this one line of code, if you have 1,000 runs, it will run your simulation 1,000 times with all the values that you created. And what it then does, the last line of code there is df or bind.fill with the output. It means that we'll actually take all of the simulation runs from, in this case, the 10 different runs, and put them all in one big worksheet. So basically, it creates it's like an Excel file with every single simulation run stacked on top of each other, with the run ID, with the times, and all the values. So basically, you've got all your output then in one file, in one data frame, and then you can actually process the data very quickly. So again, you could actually use something like Vensim or Stella to do all the sensitivity runs for you and output that to a file. But again, if you don't have access to that functionality, you can create this in OR. With a few lines of code, you can actually run the sensitivity. The apply function is a very powerful function in OR, and then you get all your results, and basically you can process the results. So in this scenario, you could have, you have for your given model, you could have maybe 200 runs, and that means you've got 200 data sets. They're all together in one piece of data, and then you can actually process the data. So for example, when you look at the output, you got 5,000 observations of 12 variables, which is 10 simulation runs, and then so basically every single, in this case the time step is 0.01, so every single simulation result is recorded, and it's all put into one very, very large data frame. But the point then is that this is what R really likes. R likes kind of big data, so you've got a lot of data in a data frame, and then you can start to use plotting functions to straight away start to visualize things. So here is the R bind puts so R bind puts it into one big data frame. So here we can see actually it's 500,000 observations, and then this is where I think you get the value from the visualization, because this function called to R then, where you can plot x, the time on the x-axis, the infection curve on the y-axis, and then you can color this by the run number. So you can take a scale of colors from the rainbow, 10 different colors, and basically then you could visualize all your simulation runs in one go. So basically the point there is that it's using the FME package along with the a couple of extra features, and then using ggplot you can then start to visualize your simulation output and generate graphs very quickly and look at the data like this. So again, I think a lot depends on how you might want to use R in the best way possible, but I do think that the plotting functions in R, and these are also recommended by the System Dynamics Review, that you can actually do very nice plots in R. So in learning things like ggplot, you can actually, no matter where your data comes from, you can find ways to visualize it in a very exploratory way. So here, for example, is again another ggplot call. Here, these are just points on a line, but with the ggplot function, you can color them by their values, and also you can, as it were, you can vary the size of the point depending on the value that it is. So for example, this shows a range of policy interventions. We have vaccination fraction on the x-axis, and we have infectivity of the virus on the y-axis. So if you have no vaccination and a highly infectious virus, you get much larger circles, because the circles represent the peak of the infection curve. So here is where you can use ggplot with some extra features to maximize the information content in a set of simulations, whereby you can again vary the size of the point depending on a characteristic. So here is the color, and also the size of the circle indicates the peak number of infected. Although I probably should have picked better colors, because in this case the small red dots are probably good outcomes, because they've a low number of people who were infected in the simulation. But basically that's a simulation of 5,000 runs. So, and then the plotting function can help you explore by adding things like the shape of the data point, also the color of it, can add extra information around the data. So basically you get more information on your graph, which you can communicate to the decision makers. Okay, so that's the that is sensitivity runs. So any questions? And again, all the code is available on the GitHub site. Okay, so I think it's useful as well to look at statistical screening. So I've written some code to do this in R, and it's because R is statistical functions available. It's very useful as well. So if we want to ask ourselves which parameters are really important, as in Ford and Flynn from 2005, we can use statistical screening to calculate the correlation coefficients between parameters and use a defined performance variable, the variable of interest, and we can do this quite again. We can do this with the model in R But again, we could also do it in a post-processing way. If we generate the results via a conventional tool, we can take this data into R and also do the correlation coefficients. So again, the point is, as a user of the technology, your interaction with the technology will depend on whether you want to write a model in R or maybe use it in a post-processing way with other tools. So the correlation coefficient is defined there. So that's R. Steps, set exogenous model parameters, calculate the correlation coefficients, select the time interval for analysis. So this is the conventional statistical screening approach. So basically, we have a set of steps that we can iterate through. But I suppose the focus here is just to show you the R implementation of this. So what we have here is, again, going back to the SIR model, it uses quite a lot here. Again, we have our min and max values for these, which are similar to the previous example. So our infected goes from 1 to 25, our contact rate goes from 0 to 7, and our delay goes from 1 to 10. We then want to run sensitivity analysis, and then with the data set, we can then do our statistical screening. So in this case, we have.
What are you doing the statistical screening for?
Yeah, that's a very good question. So it's like a model analysis technique. So it's probably not as important for smaller models, but if you have a large model with lots of parameters and you're trying to figure out which parameters are really active at a certain time of the simulation, the correlation coefficient helps you narrow down which ones are most influential. So basically, we see in a moment that, for example, that the effective contact rate in this model is very highly correlated as the epidemic takes off, but then it kind of dwindles off again. So it gives you a normalized value between 1 and -1 for any parameter in your model, compared to any of the variables in your model, which can give you insight into what's driving the behavior. So it's a nice technique because all you need really is to run the model many times with sensitivity analysis, and then take that data set and then do the statistical screening on it, where you have a variable of interest against a parameter.
Have you ever taken these correlated variables, go back and look at, say, a loop analysis or loop diagram and find that these are variables lying on certain points of the causal loops, or the intersections between what might switch dominance in a system or lie upon a balancing feedback loop that switches a positive feedback loop?
Yeah, exactly. I mean, that's the whole idea, that you would actually take this analysis then and go back and look at the feedback structure and see, is it obvious from the parameter, and maybe it's a key parameter in the feedback loop, and then that gives you an insight into how it's behaving. So it's one of a branch of, there are other model analysis approaches as well, and this one, it is, it's quite heuristic, so you can actually run your sensitivities and do the analysis quite quickly. But I think it's important to use the information to go back to your feedback structures and then to see, which parameters and which loops are they influencing and how the model changes over time. So it really is, from that point of view, to help you gain insight into the model itself. And I would imagine that, I mean, Ford's paper is very good, like Andy Ford's and then David Ford's afterwards, but in terms of, if you have a large model with lots of parameters and variables, this could give you, like a quick analysis of which parameters are really influencing at different points in time. So I think it's very valuable from that point of view. And like at the technical level then, there's a little bit of R going on, so you have to take your simulation, and what you can do then is you can, if you have a very large data set, conventionally it's organized by run number and by time. So say for run number 1 at time 0 and time 0.25, and all the way to the end of the first run, and then run number 2. But in R, for statistical screening, you want to split this by, you want to organize it by time. So you want all the observations at time 0, as it were, stored together. So in R has nice functions for doing this, so you can split the data based on a factor and basically reorganize the data set very quickly, and then you can process that.
We have a question from the audience here that's on message. I just want to read it out. The statistical screening, could you apply a rolling window to explore time-varying correlation among variables? That's from Fred Couts.
A rolling window.
Time-varying correlation. Basically, can you use something to explore time-varying correlation among variables?
I'm not sure I follow the question.
The question is, and maybe Fred, if you could clarify in a message here, I don't think Fred has a microphone. Could you apply a rolling window to explore time-varying correlation among the variables?
A rolling window. I'm not.
Jim, can you hear me?
Yeah, we can hear you.
Yes. So, the whole notion is that instead of taking a fixed time series set of data to see what the correlation is over that time window, correlations among variables may change over time in the simulation, right? Mm-hmm. So you can approach that from the standpoint of saying, okay, my look back period may be a year on a 20-year window, a 20-year simulation, and I want to just see how the correlations among variables are shifting over that 20-year simulation period, and still have some insights as to how things are correlated within that 1 year look back period.
That's a good question. I mean, I wonder is screening the right method for that? Maybe some kind of time series could shed light on that as well.
Right.
I guess to be honest, I don't know the exact answer to your question, and maybe if I go through the rest of the solution, it might become clear to you whether it would fulfill your requirements. But there could be maybe time series approaches that you could use on the data as well. Maybe things like autocorrelation over time that could be useful as well, although I haven't explored those in great detail. But I know there's a paper by Yaman Barlas who looked at using time series methods to analyze data as well.
Oh, good.
Okay.
Thank you.
Great, thanks. So we can split the data set into times. So these kind of functions, I think, if you spend some time at R, you get the payback in terms of being able to use these kind of functions to process the data very quickly. So by splitting the data on the time, all the data is organized into all the different time buckets, and we can then simply just do our correlation coefficients on that data. So here's another very useful function in R. So some of these functions I think are well worth learning. It's the sapply function, where you can actually take in a list, which is like a vector of values, and you can apply a function to the elements and get a result back. And again, a thing about R as well from an analyst point of view is if you learn these simple functions over time, that you can write one line of code that does some analysis that if you're programming maybe in Java that might take 10 or 12 lines. So you can actually write nice concise instructions as well. So here's an example of some code where this gets the mean of a number of values. So basically sapply will take a function, which in this case is the mean, and a set of input, and apply that function to every input. So basically, it gives you a way to process things very quickly. So I know this is maybe a little bit technical in terms of the code, but basically this line of code is your correlation coefficient. So we take in the data that's been split by time, and we simply apply the core function to where we have the variable of interest as one value, and then the parameter as the other. So basically, we have this. We have our data set, and there are variables there. One is called the number infected. The other is your parameter, and we can create the correlation coefficient very quickly from this. So again, with R, if you spend some time just going over these things like sapply and split, and look at the correlation function, you can do this analysis very quickly and write a script that will do your statistical screening in a very convenient way. So basically, this is the kind of output that you get. We have the average infected over time on the top graph. So that's the average over, I think, 200 simulations. And then we have our correlation coefficient for the CE parameter. And it shows it's very highly correlated, which you would expect at the time of the infection curve getting to its peak. But then it kind of wavers after that. So basically, what you then get is a time series of the influence of the parameter on the variable of interest. And what's nice about this approach is it's normalized between 1 and -1. So basically, we can do this pretty quick and see this extra analysis that could be used again in a post-processing way, because if we run a simulation and store all the results in an Excel file, we can bring this into R and run this script very quickly, and it's only probably 5 or 6 lines of code to get this kind of output. So it just shows that I just picked statistical screening because obviously the stats side is R is very good for that, but there's so it's a nice way to look at your parameters and seeing which ones are the most influential.
I have a thought. I don't know whether it's productive or unproductive thought. But I was thinking that the behavior of the systems and of course our models depends on the state. It's a state-dependent behavior. Of course, it's visualized over time.
Yeah.
And then we are doing the statistical analysis, which is an analysis of the behavior over time. And I would find it very difficult to deduce any causal connections from any type of statistical analysis which is done over time. Because the causal analysis is state related.
Yeah.
The statistics are time related. And it's kind of difficult, at least for me, to deduce any causal relations from the statistical analysis that pertains to time. Does that make sense?
Yeah, I think in terms of I think in using this technique, it's important to go back to the structure of the model. And so, in terms of while if we look at it's really the technique is showing us that over time, over many simulation runs, that the link between the one parameter and the variable of interest is very high at a certain point in time in the simulation. But then, I mean, to make this technique work very well, you need to go back and say, well, where is the parameter in the model? So we can see it actually, it's on the top right-hand side. It's the effective contact rate, which impacts beta, which impacts lambda, which is part of the feedback loop. So it's really just, I think, a way to generate discussion about which of the parameters is active at a certain time of the simulation. And
I guess another way to phrase the question is, if the system is initiated in a different state with different values in the stocks, would that still show a high correlation because it would now be running in a different state? And over time, would it still show interest? I mean, we know in this one it probably would because we already know the answer. We know it's part of the feedback loop.
Yeah. I suppose in this case we're sampling many values, so there's 200 simulation runs that's driving this this result. So and then the average then is just the average number, the average infected over time, and then from that then we have our correlation. So I mean these are very good points in terms of techniques that we can use to analyze models, and I think the points are very well made. And I think the main thing I'm showing here is that for a technique such as statistical screening, whereas before you could do this in Excel as well, but it's probably a lot of overhead. But for a short overhead with a short script, you can generate this data quite quickly, and then it becomes part of the model analysis dialogue where you look at the model, look at the structure, look at the states, and see, this is telling us that the effective contact rate is very important in the first 5 time units. Why? And then you ask the question, why is that the case, and what's driving that behavior? So I think it's just another dimension with which you can look at the stock of flow model. But fundamentally, with these techniques, you need to go back to the model, you need to go back to the feedbacks, and you need to see what role the parameter has in the feedback loops.
We're kind of running to the top of the hour. Are there any more slides that are crucial that you want to get to?
Okay, yeah. The other thing is just R Shiny. This is the model we did for a project, and it just basically, okay, I'll go through quickly. So basically, you can actually, in R Shiny, you can put together a nice web interface and show maps, and then show output, etc. And it's a little bit of overhead in terms of doing things, but it means you can actually display your simulations, share them over the web, and even make them into a decision support type tool where people can run the simulations. So that was really the last piece. So R Shiny is a very nice tool, and it's a way to visualize your simulations.
This is one that I think is one of the main benefits of R, is the ability to put it on the web, because at least with Vensum, that's always a challenge, is to get a web interface.
Yeah, exactly. And what you can do then is you can put dials together, you can put dashboards, you can have tabs, but basically behind it, yeah.
I think this slide alone and your utility that can convert a Vensum equation structure and allow you to get it onto the web is worth the
and
value.
Also the geographic representation. I think that could be very valuable, because that's not available in Vensum or Stella.
Yeah, that's a good point. I forgot about that actually, because we can use R functions for mapping, and we can put points on it. We can draw kind of filled-in diagrams. And
I've done simulations in Iraq and Syria, and creating the map is a hand-drawn affair, extrapolated from percentages in Vensum. It's a real pain. So no.
Okay. Yeah. So
are there any other closing questions before I allow Jim some closing comments from the folks in the audience? Okay, go ahead, Jim. Any closing comments?
Yeah. Is there a question there? Yeah.
I have a question about hybrid modeling. Can we do hybrid modeling in R, for example, combining agent-based models with system dynamics models? In theory, I think we should be able to do that, but I'm not very familiar with R, so.
Yeah, that's a good question, and I just discovered only actually yesterday that NetLogo has an R interface as well, so you could.
But I'm aware of that tool. But as I understand, you need to create your model in NetLogo first, and then use R NetLogo just to communicate with that. So other than that, I mean, is there any way to build your model in R? I mean, agent-based models in R, and to connect them into your to your system dynamics models?
You probably have to code it all up yourself. I mean, but R does have a thing called iGraph, where it can help you with the network. R has matrices, but I think to get the logic and the discrete event engine going, you'd have to write some stuff yourself, I think. But the model that I showed you can do disaggregation quite easily. So that means you could have a disaggregate model, but it would still be stocks and flows. But I think that's a good question. How do you, as far as I know, I don't think there's a discrete event simulation within R, although there could be. But if you didn't have that, you'd have to write your own code for that, which would be probably tricky enough, I'd say, to get that working.
Thank you.
Okay. Thanks.
Thank you.
So I think we're we're out of time now, are we? Yeah.
Yes. Thank you very much, Jim. It was an excellent presentation. It looks like he's got the GitHub web address at the bottom there, and you said you've uploaded these slides to that GitHub?
Yeah, I have. Yeah, the ones that are there from last week. I'll just update the most recent ones from today up there as well. And I mean, I'm very happy to get emails from people, and I think the questions today were really good, and it's good feedback in terms of how to position this and how best to use it. So I appreciate all the comments, and it was great to get a chance to talk to you.
And we're going to go ahead and stop the recording, but we're going to upload the recording onto the Google Drive, and we'll make a link available so that people can see this. And Jim, if you want to put it out on, we'll have a YouTube channel for the SD Club where it'll be made available. If you want to link to that too, it may be a way of spreading the word a little. Okay?
Okay, that sounds good. Okay.
All right. Thanks, everyone, for this meeting. What's next week's meeting for CLM? Who's presenting?
I haven't decided.
Special guest star yet to be announced next week. Thanks, everyone.
Okay. Okay.
Okay, bye.
Bye-bye.